Kalorička jurisprudenza, vedere, vedere che G. Eric, we wait 5 minutes and then we start.
Okay, that's fine by me.
Eric, we can start, I think.
Okay. Give me just a second to get everything ready on my end. Okay, can you see my screen?
Yes.
Okay. So let's move on to the final topic or final couple of topics for this workshop. Before we actually move on to post-processing effects and the universal render pipeline, the first hour of today's workshop will be covering the last form of tracking you can do in augmented reality. So yesterday we covered a couple of tracking methods. The box standard tracking that comes right out of the box with AR Foundation and AR Core. Afterwards, we covered plane-based tracking and interaction, and then AR anchors. Today, we're going to be using a different method, which is much more commonly used, or was much more commonly used a couple of years ago. But with these new tracking algorithms, it's slightly falling out of favor. But some applications still do employ them because it is very easy to pinpoint the exact location of an object that you're tracking, as well as you can update the location of the tracked object continuously. So you can basically track something that you have in real life with these tracked markers. And what I'm talking about are either tracked markers or tracked images. And there are algorithms for marker tracking which are very fast, and quite a couple applications use them. But AR Core and AR Foundation both use image-based tracking. So it's a lot more versatile, but unfortunately it's slightly more computationally heavy, and the tracking can be lost sometimes. But it is a lot more seamless in its implementation compared to marker-based tracking. So that's what we'll be doing today. Since we'll be tracking images, we will also need some sorts of images that we will track. In my case, I have my old university access card that I have taken a photograph of with my phone. And then I just cropped out the actual image itself. So I have something like this as one of my images. But if you don't have an actual physical image that you can track, you can also just have an image on your actual monitor and assign the tracking to that. So the end result is your tracking algorithm will track the image on your monitor display. But for both cases, if you have like these tracked images, it's a good idea to, if you have a final implementation, to have these images as matte as possible, so they don't have any reflections or shine or illumination, because that affects how well the tracking can work. Now I'll just start up my project right now. I did try and look behind the scenes which exact tracking algorithm AR Core uses, but there was no actual reference of a specific algorithm. There are multiples available, things like SIFT surf and orb feature detection and stuff like that. But if you actually work with image processing, then you will come across these a lot more. I will also set my preferences back to the larger screen size and set the theme to light. But essentially how this process works is that we give our code a reference image. So let's say this is our reference image, or in my case here in this folder, I have this reference image. The code will first run through this image and run its feature detection feature detection algorithm. So that will detect points of interest in this image. And it's a good idea to have an image that's less like this image, but more like this, where you have lots of unique locations on the image. So crevices and transitions from one color to another, these are very good, very unique features to detect. On the other hand, if you have an image like a barcode, then you have lots of repeating features, and those are not that good for tracking. So actual images are much better. And in some cases, even logos are quite terrible in terms of tracking. So let's get to our actual project. First things first, we will create a new scene so we can keep our previous anchor scene alive. So go into the assets and then scenes folder. I'll just minimize this a little bit. So go into the scenes folder, click the plane scene, and then Control D, just like yesterday, and rename this new scene. And we'll call this the image scene. Let's double click on this scene so we have it active in our hierarchy. And let's remove all of the components that we will not be using. So the scripts that we wrote for the plane detection we won't be using, the pointer we won't be using, and again the raycast manager and the plane manager. So we have a clean scene now. So this is exactly what we did with the anchor scene when we set that one up. So it's just remove the script in the that you added either onto your AR session origin or your custom scripts part, remove the pointer, and remove any components on the AR session origin besides the AR session origin script itself. Now, after you have done this, we need to go to our build settings. So File, Build Settings. And again, just like yesterday, we have to press Add Open Scenes. And then we remove the check mark from our anchor scene. Now, if you do add these check marks here, then you'll notice that the scenes have indices next to them. And oftentimes when you build a project, then the scene with the index 0 will be your main scene. So if you start a project, then that's the one, if you build a project and run it on your phone or application, then the scene with the number 0 is the first one that is initialized. So if you want to transition between scenes, you need to keep note of that. But now that we have the image scene added here, we have effectively gotten to a point where we have a base project that we can start working with. One thing that we will need is we will need to go to the AR session origin, and we need to add a new component. So this will be an AR component, and we need to look for the tracked image manager. So the tracked image manager is the out-of-the-box image manager script that handles tracking single images or multiple images, and then it places a prefab that you have signed onto that image. So it makes the image act as a cursor and then places any of your prefabs on top of that cursor and aligns them based on the location of the cursor. The AR Tracked Image Manager also has a couple of fields here. The prefab we can assign right away. We can just take one of the prefabs that we have created ourselves, like the spawned object one, which is the cube or the sphere. So I will just take the cube and place it here in the tracked image prefab. But we also have two more fields. One is the max number of moving images. So how many images are we tracking at a time? We can set this to 1 since we only have one image at the moment. And the second one is a serialized library. So this is not a reference to a specific image. This is a reference to a list of images inside Unity that have specific dimensions associated with them, as well as specific names associated with them, which means we have to create this. 0, I think it means none. The maximum, if I remember correctly, should be 20 images, or it was 20 images at the same time. But for now, we will just set this to 1. Then we will have to create a reference image library. So go back to our assets folder. We'll create a new folder for images. And here in this folder, press right-click, create, go to the very bottom on XR, and there is a reference image library. There is also a reference object library, but as I mentioned, I think during the second day, object tracking and detection is something that is currently not supported on most Android devices and is only supported for a couple of the newest iOS models. So we will only use the image library tracking. You don't have to rename this. We can just keep it as is. And this image library is now an object where we can start adding our images. Now, first things first, we need to add an actual image into our project. For that, you can just quickly Google an image, or if you have already some image that you have in the real world and you can take a picture of it and then quickly crop it and paint or something, then this would be an ideal place to do it. So I will just use the image that I have. So it doesn't matter what sort of an image you have. And I will just drag them into this folder. I'll give you all a minute or two. So if you don't have an image, you can look up an image. And for those of you who want to use the exact same image that I'm using, then I will upload this as well. I will not upload the card image though, since obvious reasons. Now, if you do have an image and you just import it, so those of you who are still looking for images, you don't have to really pay attention to this or worry about missing anything. But if you import images into Unity, then they come with a lot of different features that you can set. So things like if you want your image to be a UI element, or how to import images into Unity. So if you have your image somewhere in a folder, you can just click and drag it into the folder structure of Unity. And if that does not work, then you can open up the actual file location of your project. So, and then go to Assets. And in Assets, you will find the same folder structure as I have right here. And then you can go into the specific folder where you want to add your image, and you can drag it there. So it functions almost identically to a normal file system, just that Unity also creates these .meta files for all the objects that you have in its folder structure. And if you add any files and then open up Unity, then it will comb through all of the files in its file structure and check if they have meta files attached to them. And these meta files set specific attributes for these files. Like in the case of image, I can choose which type of a texture Unity should consider it. Either is it a sprite, or if it's a normal map, or how it should filter it if I'm scaling it upwards or down, or scaling it down, and what size is it should consider it when using it as a texture. But for the image tracking one, we don't need to set any parameters for the imported image. Now, after you have imported an image into Unity, you can check the reference image library and then click and drag your image into the first slot. You can add multiple images, but I will cover that later. Unity will assign the same name that you have as the file name, but you can change this. So I'll just name this to card, or card image in my case. And for image tracking in particular, we need to know the actual size of the image that we're going to be tracking. So this is important if you have your camera and it's looking at the image. So if you have your camera and it's looking at the image, then depending on how far your image is from the camera, then your application needs to know how far away to render your object, or where to set your actual location in space. For that, there's this option here to specify the size. And the size will be specified in meters. Luckily, I have already measured the size of my card here. But if you have an image on your screen, so let's say we will be using, or we can use this image of a bird here as our tracked image, then I would just have to physically look at the size of the image on my monitor and just estimate, is it about a couple centimeters in this direction, a couple centimeters in that direction. In my case, I can even use this card that I have the size already measured out for as a reference, so I can measure out the actual size on my screen. And if you have something that you know the length of, then you can always scale the image to fit that particular size. So this is good for quick testing if you don't have an actual separate physical image. In my case, the physical size will be 0.0524 meters, and it will automatically set the Y. Next, we can go into the AR session origin and take the reference image library and just drag it into our serialized library reference. And if we run our project now, I guess I can build it right now to demonstrate how it works. Connect. And then go to my build settings, and I'll quickly build the project. Now, this current setup that I'm using is all fine and well for most simple applications that you want to do with image tracking. So it will just track one image that you give it. But if you want to make a slightly more complicated project where you have multiple images being tracked and you can interact with them, then you will have to do a couple modifications, and I'll show you exactly what you need to do. But for now, it should finish right about now. So if I run my application, so the cube is clipping into my actual camera. Oh. It's kind of a very reflective surface that I picked here, which is not very good, but it will track the actual object in real time. So if I start moving this around, then it will also move the tracked object around. In my case, my tracked image is kind of very reflective, so it's not tracking very well. But if you use like a matte image or a matte picture, then the tracking will be quite accurate, even from a slightly larger distance away. And this is one way of having these smaller interactable interfaces with Unity. A small example of this would be if you want to build an application for a store that sells, let's say, watches. Then you can have the user put a specific marker or a sticker on their hand, and then if they run this application, they will see the watch being cast on their wrist, so they can do this checking of different watches from home. And if they move their hand or arm, then the model will track the location of the arm and continue following along with them. But this application does have its limits with the current implementation we have. And that is, we can only track the way we set it right now, we only track one image. If we want to have multiple images, well, we can add another one here in the reference library. So I will just add my second image here. I can specify the size by using my card as a reference so I can measure it on the screen. But if we go into the AR session origin and we change the max number to 2, then our application will now track both my card and the bird image, but it only has one prefab that is being displayed. So no matter what image I'm showing my application, it will still assign the exact same 3D object onto the tracked image. And in most cases, if you have multiple images being tracked, that is not what you want. So in order to mitigate this, we will have to write our own script that accesses the tracked image manager, gets the IDs of the images that are currently being tracked, and then assigns specific prefabs based on those IDs. So let's get to it. First, let's go to Assets, then go to Scripts, and let's create a new C# script. And I'll name this Multiple Image Manager. And then you can just open it up in Visual Studio. So this script will be slightly more technical compared to the previous ones, but I will still attempt to explain everything that is actually going on. So first things first, every time we're writing scripts that should interface with the AR Foundation libraries or the functionalities, then we need to import them. So XR AR Foundation, and using AR subsystems. Now for the script, we will need some sort of a reference to all of the models or prefabs that we'll be showing. So for that, we can just create a simple list where we can put objects in. And there are two types of lists, or sorry, the previous one was a list, but this one is an array. The reason we're using an array instead of a list this time is in the Unity editor. If you have a, oh, sorry, we don't have the actual script attached to anything, so I will add it to the custom scripts just to show it. So if we have an array, then we can define how many objects are in that array and then put the objects here through the editor itself. But if we have a list, then this will be slightly more complicated and the functionality will differ ever so slightly. So this is just in order to make it easier for us to edit later. And the reason why we're using lists if we don't want to input values ourselves, is because lists are dynamic, so we can change the size of them at runtime, while with arrays, we have to set the size at the start. So next, we need a reference to the tracked image manager itself. So we need a reference to this object here. So it will be a private AR tracked image manager. And we can assign this at the start. Using find object of type. So this will search through our entire Unity hierarchy. And since we only have one AR tracked image manager, this is very fine to use. And we will also need one more object or a type of a list, and that is a dictionary. And the reason why we need this dictionary is we will have a list of objects, and through the AR tracked image manager, we will get reference names of the images that are currently being tracked. And somehow we need to tie our reference names and the actual models together. So we need some way of looking up an object or a game object using just the name of the image. And for that, we can make a dictionary that has the image names as the keys and the models as the values. And we can initialize this dictionary here at start. Just a new dictionary with that typing. This means if we start the application, we will have an empty dictionary that we can start adding objects into. And in our start function, that's exactly what we're going to be doing. We are going to iterate through all of the game objects that we have added here. So in the editor, if we add any game objects into our array, then we'll iterate through that array and add every single game object into our dictionary. And we'll use the names of the game objects as the lookup keys. So that way we have a form of control over what sort of an image is going to be tracked by what sort of an object. And it will not be dependent on just the order of objects added to the list. We'll use a for loop. This way, we're iterating over every single object in our list, or sorry, in our array. And since these are currently prefabs, we need to initialize them as well. So an AR object, we don't need to set the location, so it will be a vector of 0. And same goes for the rotation. So a quaternion identity. Instantiate. There we go. Now that we have created the model, let's also save it to a reference so we can add it into our list. Sorry, a variable so we can add it to our list. Make this multi-line so it is visible even if it goes outside of the screen. And next we need to take the name of the object. We're just assigning the name of the prefab to the name of the object that we just created. Now, the reason why we're doing this is if we create new prefabs, then by default, their name will always contain the name clone. And for our tracking purposes, we will only be creating a single instance of the prefab. And since we're referencing the object by name anyway, then it's a good idea to have the same name. And then we can add this to the dictionary. Let's use the name of the prefab just in case. And then add our object. So what we're doing right now, we're just taking in this array of array of models that we're predefining in the editor. And as soon as we start the script, we're taking all of those models and adding them into a dictionary so we can reference them by the model names instead of some indices or something more complicated. Now, next, we will need a function that will actually handle our interaction with the AR tracked image manager. And since AR tracked image manager, we can't really write code into the AR tracked image manager, or we can, but it's not really recommended, then we have to use a form of adding events into the AR tracked image manager. So the AR tracked image manager has an event handler that executes every single time it finds an image that it's supposed to track. And we can add a function call into that. But in that case, we need to specify a couple things for this function. Namely, the inputs need to be correct, and then we need to add it into the AR tracked image manager itself. So let's first define the function. So we'll just name it onTrackedImageChanged. The name of the function itself shouldn't matter, but I know the inputs and the output do matter. And in the inputs, we need AR tracked image changed events arguments. Tracked image change events arguments, and we'll just name this event args. And if we have this function, then we now need to add it into the AR tracked image manager. so that it actually calls this function. So we can have a void on enable. So void on enable is a script that is called as soon as this entire script has finished its initialization and has been enabled. So we can take the reference image manager, or a reference to the image manager, and the image manager itself has a field called tracked image changed. And this field handles all of our events. And the way we can add our new function to this is plus equals and then the name of our function. So it is a bit arbitrary, but this is the way how you add event calls into the tracked image manager, and a couple other libraries use the same layout. And if we want to remove it after we're done, then on disable, and minus equals. So this is just a bit of fluff that we need to add so that the tracked image manager would call this function every time an image is being detected on the screen. Next, we need to go through this input for the event arguments and actually act upon depending on what the image tracked system is detecting. So event args has a list in it called added. And this is a list of tracked images. So if there are any new images being tracked, then they will be added into this list. So we can iterate through this with a for loop. So AR tracked image, tracked image. So these are all of the images that have, so if we take our phone and it detects a new image at the start, then this will go into the added list, which means that it has been detected for the first time. And we will create our own function that will handle what we do when we detect an image. We'll give this tracked image in there so we can handle the specific image later on. So for now, we can just call this function that we will create ourselves. Now, the event arguments, they don't only have added, they also have two more for cases when you update the location of your image or if you remove your image from the screen. So we need to have references for those as well. For updated, we will just use the exact same layout. So in both cases, we'll just update the location of the model that's being tracked. We don't need to change anything here, only the reference here. And for removed, it would be nice to take the model that's currently being detected and remove it from the scene completely. So this way we can take our AR objects dictionary we can take the tracked image and we can take the name of the tracked image. So this is how we can look up from the dictionary the specific model tied to the image that we are currently tracking. And all game objects have the ability to set if they are active or not. So this will disable the object in our scene. Now, in case we are actually detecting the object, we can go into this function and we can look up which object we are detecting and then update this object's position and rotation. So first, let's take the name of the object that we're detecting. It actually should be a reference image here as well. Then let's take the position of the image that is being tracked. We'll put the tracked image, reference image, position. Oh, not the reference image, but the tracked one. Yes. And the rotation, which should be very similar. So with this, we have the name of the image that we're currently tracking, the position of the image, as well as the rotation of the image. And now we can look up the actual model associated with this and assign the rotation and position of that object. So let's fetch that model. So now we have a reference to the model. Just to be safe, we can also make it active. And we can set the position and rotation of our model. Before I continue, I will also quickly check if there are any errors, and then I will upload this script to the drive. So you guys who missed a step or fell behind at some point, you can just download the same script. So this is multiple image manager. So just to go over it one more time, we are at the start of the script. We are assigning the AR tracked image manager, and we're creating a dictionary. We're populating the dictionary. Then we're creating a function that handles the events coming from the tracked image manager, and we're assigning it to the tracked image manager. And then depending on what the tracked image manager returns, so either it has detected a new image, or it has updated it, or it has removed a image, then we will call an update method that will take the location of the image that's being tracked and assign it to our models. Now, next, what we have to do is this new script that we have just created. We have to attach it to a game object somewhere in our scene. So in my case, I have this empty game object called custom scripts, and I can just drag and drop it onto the multiple image manager. And now we need to set the amount of models that we're going to be tracking, and then place the models in this list. But do note, the way we currently implemented the script, it references the names of the prefabs that we are deploying based on the images that we're tracking. So that means that the names of these images here and the names of the prefabs need to match exactly for them to work. So that means we can either rename the images in the reference image library, or vice versa, we can rename the prefabs based on the images that we have in the reference image library. So I will do one of each. I'll take the birds with arms script, or the name of that one, go into my prefabs and rename the sphere into bird with arms. And for the cube, I'll take the name of this cube. I'll go to the reference image library and rename the card. So whichever way you rename them, the name here and the name of the prefab need to match exactly. And capitalization and underscores and stuff like that, all of that matters. It needs to be a one-to-one string name. I'll now try and build the project and see if this functions all right. One thing I do need to do is the image that I'm using. I have currently assigned it in the code that the x-axis is the same as or the width of the image is the same as the height of the card that I'm using for my second tracking. So I need to reference these two and just manually align them to be of a similar size. And after I've done that, I'll open it up here and enable USB debugging so I can upload my script. End layout group, begin layout group must be called first. It rings a bell, but I don't remember right away. At what point are you getting that error? In the editor itself? In the editor, okay. Does it state which line you have this error, or is it to do with the scripts? While I'm here, I can show you the current implementation of the code. So I'll just pick up. So I have the cube being tracked with my cart. Again, this is a bit shiny, so it isn't tracking that well. And then I have, oh, yes, I have, I wonder if I go inside of it. So currently, I forgot one step. So in the AR session origin, I need to also remove this object here. So this will be this is our original object that is assigned by default. We do have the number of images being tracked set to 2. I'll just quickly reference that the sizes are in fact okay, and the script is okay. And the prefab sphere is smaller, yes. So yes, in the AR tracked image manager, you also have to remove the tracked image prefab that you have here, because by default, it will still add the models onto your detections. And find object of type is independent of location. So this should be fine. Mm-hmm. And if I have the bird over there, it should detect and place the sphere. Okay, let me see if I have maybe disabled the game object or if I have made a typo somewhere in the code. The object itself should be visible. I'll do a quick edit in the code to reference it based on what I have tested previously. I wonder if there is a small problem with the dictionary implementation. Oh. I'll try and rename this to awake. So this is going to be executed at a different point instead of start, but this should not have a profound effect. And just in case, I'll comment out the removal script in case this is prematurely removing the objects that we're being supposed to detect. Because I do know that the image tracking library is kind of finicky in its implementation of the removed and added. So the custom script does have two objects attached to it. The reference image library has two images that do have the correct sizes, and the tracked image manager has a reference to the correct system. Let me just try building it again. So USB debugging enabled. Build and run. I'm assuming this is something very, oh, yes. So you get the cube for both images if in the AR session tracked image manager, the prefab is still set to the cube. So this means the previous version that we had is still placing objects on both instances. I'll test right now if it can. Okay. So it detects my cube. And does it detect? Yes, it detects the bird. So now I have, oh, you guys can't see it, but okay, I have the sphere being detected on my monitor. So if I move it around, it gets detected. And the cube is also detected, but the card is very reflective. So you can see why it's a good idea to avoid reflective surfaces. I'll quickly update the code because I am assuming that previously, because I had this typo here, then the remove function was not actually functioning. So through my previous test, this remove function is kind of finicky sometimes. And if it removes the objects that you're working with, you might not be able to get them back. So this just requires a bit of finicking behind the scenes to get it working regardless. But I'll take the current script and upload it, and then I'll show you the setup of the rest of the parts of the code, or not the code, but the Unity implementation itself. So I'll update the existing code. So yes, if you have added the custom script that we just created into the scene, then first you need to, yes, add the models. You need to make sure the names of the models are the same as the reference images names. And lastly, in the AR session origin, you have to make sure that you don't have an image prefab being tracked already. Now, this won't stop your own models from being rendered. This just means that if you have something that is being assigned here, then it will add on top of your original model. So you will have two models intersecting with one another and they're being rendered in the same place. For my case, since I have the cube, then I won't be able to tell which cube is being rendered since they're overlaid in the same location. And for the sphere, the cube might place in such a way that I can't see the sphere. And if I go inside of the cube, then the intersection will also remove the sphere from my view. But this is essentially a very simple implementation of how to get multiple image tracking. I've seen this being used in quite cool teaching tools for younger children. Things like teaching the table of elements or chemistry to children by taking different elements on different cards. And then by moving these cards together next to one another, then based on distance, they would react and create a new different model. So there's lots of potential here for projects that you can create. But for now, I'll just exit out of the program that I have at the moment, and I'll upload the project into the folder. And after I have done that, so my project is here. And after I have uploaded it into the folder where we have all the rest of the projects, then we can go on to the first break. And after the first break, we will come back and we will start working on post-processing effects and how to use the universal render pipeline and what the universal render pipeline actually is and why you should prefer to use it in any scenario that you plan on creating. Oh, I need to also close this. So thank you all for your attention, and I guess we will see in about 43 minutes. Yes?
Can you please write the time when we come back?
It should be, what was it in your time? 11:30 your time. Oh, sorry, 11:30, that is... No, wait, what?
Now here is 11:20.
Oh, okay. I think I went over my time then, or I'm confused now.
Yeah, at what time you think we should start?
Let's just start 15 minutes from now or something. And have just a quick break. Yes, I'm here. I'm here. Give me a quick second and I'll set things up on my end. Okay, can you see me all okay? Okay, perfect. So I'll just go back to the project. Now, thus far, those icons are tiny. Thus far, we've been exploring the different functionalities of AR Core and by extension AR Foundation, and what you can do in augmented reality or how you can track different objects in augmented reality. The interaction part and what you actually do there is all up to you, because I can't really give you ideas since all projects are very different and require different components. But there is one topic that I can still cover that is very relevant to quite a lot of augmented reality based applications. And that is the aspect of realism. Now, this part that I'll be covering first does improve the visual quality of your project by quite a substantial amount, but it is something that you should still do even if you don't plan on having very visually high quality models. And that is switching from the Unity's default render pipeline. So the default rendering algorithms Unity uses over to their newer implementation, which they call a universal rendering pipeline. So it's essentially a pipeline that increases your frame rate in rendering by quite a bit. It reduces the amount of vertices that are being rendered that don't need to be rendered. And it does have a lot of optimizations in the backend. And additionally, it gives you more functionality in terms of creating your own customized shaders and surfaces and materials. And the reason why it's called Universal Rendering Pipeline is because this is something that Unity and Unity developers are pushing so that it would be used on all platforms in the same manner. So Universal Rendering Pipeline is something that you can use on Linux, Windows, Mac, iOS, or Android, and even a couple other formats that Unity can build to. And if I remember correctly, then the newer versions of Unity, they will most likely come with the universal render pipeline built into it by default. So it's hard to start a project without the universal render pipeline. But since our project currently doesn't have it, we will have to add it. So the way we do it is we go into Window and we go into Package Manager. This is the same location we had the AR Foundation and AR Core packages. Let's wait a second while it fetches a registry. And then make sure you check the Unity registry instead of in project. Otherwise, we'll only see the packages that are currently already installed into this project. And we can type universal. What you'll see is universal RP. So this is the universal render pipeline, or URP for short, and just hit install. So the render pipeline is something that works in the behind the scenes and tells the editor and, sorry, not the editor, the program, how to render stuff on your GPU and how to optimize and which parts of your scene should actually be rendered on the CPU and how they should be rendered on the CPU. Sorry, not CPU, GPU. And for phones and devices that don't have a GPU, it still has some optimization benefits tied to it. So if you have the universal render pipeline installed, or if you don't, you can just continue while it's installing. Yes, this is the part between OpenGL or Vulkan. So if you have something rendering on screen, this goes into the shader part, and the shader part defines which vertices are rendered and how you render each single pixel between the vertices. And that information is then passed on to either OpenGL or Vulkan, which passes it on to your actual GPU, so the hardware side. So this is a layer between there. Now next, we have to go into our project folder and create a new folder. And we'll call this rendering. And in this folder, we will have to create two assets. So press create, and then scroll to rendering. So rendering is here in the upper middle portion. We have universal rendering pipeline. And the very first thing is the pipeline asset forward renderer. And if you just click it, it will create the forward renderer. You can rename it, but I will just leave it as default. And if you click away from it, it will create both the universal rendering pipeline assets that we will work with. So again, this is create, rendering, universal render pipeline, and pipeline asset. And this creates two assets. One is a universal rendering pipeline asset underscore render, and the other one is just the universal render pipeline asset. And they are tied together or tied to one another. In the universal render pipeline asset, we already have a couple of variables that we can set. But right now, these won't be applied to our project because our project hasn't been switched over to the universal render pipeline. It just has the packages installed to it. In the render asset, we have to add a component to it. So out of these two components that we just added, select the underscore render, and then press add render feature, and select the AR background renderer feature. And you don't need to change anything there. What that essentially does is once we start using the universal renderer pipeline, then this communicates with AR Core or AR Kit and tells them what is or how to handle the background so that for the phone it's transparent, while in the scene how it should be rendered. Otherwise, you would not have a transparent background and your application wouldn't function as it should. Next, we have to go to the project settings and actually set the render. So we'll go to File. We'll go to Build Settings. And in Build Settings, go to Player Settings. And in the Player Settings, from the top, the third option is Graphics. And in the graphics, the first option is the current render pipeline. If you have none, then this will be the Unity default. And we will select the universal render pipeline asset. And with this, it should switch over the project. And we can close out of this. After we have added, so let me just show that once again. So build settings, player settings, graphics, and the first option here is our custom universal render pipeline asset. After we have added that, we can tweak a couple functionalities in the render pipeline asset. We can add high dynamic range. So under quality, there is high dynamic range. This means how much depth there is for the color values. If your device that you plan on building it to supports high dynamic range, so most newer smartphones do support it. Some older ones don't. So it would be a good idea to first verify if they do support it. This just makes it so that you have richer light tones and richer dark tones so that they're not cut off at a specific value. And another variable that we can set here is the shadows distance. So we can just set this to 5 meters in my case. This is just because if we have an augmented reality application, then we will most likely not look at shadows more than 5 meters away from the user. So there's no point in wasting processing power to start rendering high quality shadows that are so far from the user that they won't be rendered anyway. Now, if your project has old objects already in it, so if we switched over to the universal render pipeline, then all materials in our project will basically break. And that is because the shader that is running behind it is not supported in the universal render pipeline. The universal render pipeline has a different format for shaders and shader scripts. And by default, Unity has its own form of creating shaders. Once you've switched the project over to universal render pipeline, then all new objects created will have the correct shaders, or correct shaders attached to them. But if you're upgrading an older project, then there's one quick thing that you can do. You can go to Edit. Then in Edit, you can go to Render Pipeline. Go to Universal Render Pipeline, and then upgrade project materials to Universal Render Pipeline materials. Now, this will not fix all materials, but it will try and fix most. So in this case, it did not want to fix this material, so we can just swap this out with a custom one later on. I'm guessing it doesn't want to fix it because it is a prefab instead of an actual object in the scene. But switching to universal render pipeline is a good idea either at the very start of the project, or if you remember when we created this project, there were a couple of options to make the scene 2-dimensional, 3-dimensional, or start with the rendering pipeline already attached. And in that case, you can just start a new project that has the universal rendering pipeline attached. But let us go on to our scenes, and we'll create a new scene. And we will start implementing some features that we can now use with the universal render pipeline, since they are now much faster than they would be without the render pipeline. So we'll take our image scene, we'll duplicate it, and I'll rename it to URP scene. I'll double click it and make sure this is our active scene. I'll remove the multiple image manager and the tracked image manager, since I will no longer need those two. And then we can start developing some things in this scene, or I will try and show you guys a couple of functionalities that you can apply in augmented reality to enhance the amount of realism. Now, one of those things that is the simplest to add is if I go into the slides I had. So I hope you can see the images on this slide. So thus far, the objects that we've been working with look like the first image here. So they don't have any influence from the background. We can add textures to them. We can add normal maps. We can add cool lighting in our scene, but this won't be, it will still be very much independent from the actual environment that we're rendering our objects in. What we can do very easily is add environment probes. Environment probes are a form in Unity, or sorry, not in Unity, in AR Foundation, that essentially samples your background and creates a lighting, like a sphere lighting system that directs light from every single direction onto your model based on what it has sampled from your environment. And these spheres update over time as well. Currently, they update very abruptly, so it's not a smooth transition from one to another. So there's still some improvements that can be made in AR Core and AR Foundation. But right now, they work right out of the box and are very simple to implement. A very useful thing where they can be used is if you have slightly or even if you have reflective or even slightly reflective surfaces that you want to show off. So in case of if you're creating a storefront for selling objects and you want to demonstrate the objects that you're selling to the buyer via augmented reality, and let's say the object that you're selling is a wristwatch, then it would be very plain for the user if all of the surfaces are just matte, or if they are shiny, then they only reflect light from a certain angle. So what the user might prefer is that it actually shows reflections of the background on your surfaces, or at least attempts to do so. So for that, all we have to do is go to the AR session origin, add a component, and search for AR Environment Probe Manager. And that's it. We now have actual environment values being detected, and they will automatically be updated in your scene. So now if you have any object in your scene, then they will have reflections associated with them based on the background. A quick way I can demonstrate this is if I create a new object in my scene. Just scale it down so it isn't as massive. And I'll also make multiples of these objects in case I don't see it in my first run through. Now, at the moment, all of these objects have a matte surface, so they're not going to be very reflective. In order to make them reflective, we have to make a material that has a very reflective element. So we can go into the folder that we named materials. We can do create and create a material. And if you have switched your project over to Universal Render Pipeline, then you can see that at the top, the shader is already automatically selected as a Universal Render Pipeline shader. And I'll just name this one mirror. It would have been a smart idea to assign the material first and then copy and paste it. But luckily, I don't have that many objects here. Now, this material has a couple properties we can set. And there are different workflows as well. Personally, I prefer the specular workflow, but the metallic also works quite fine. And it is usually the default that most people use. And in the material workflow for the standard shader, there is the smoothness element and the metallic element. So metallic denotes how reflective an object is, and smoothness denotes how much of the reflection is directed back into the camera or if it is scattered around. So for instance, we can bring the metallicness very high and lower the smoothness. Or sorry, increase the smoothness, not lower it. And in the small demo here of the material, we can see that if we increase the smoothness, then the light source that in this scene is actually a point goes into a point. And if we bring it backwards, then it gets scattered and becomes larger. And metallic just shows if it is reflecting the background or if it is mostly showing its own color. Now, if we take this scene and go to our build settings, let's also add it into the open scenes and select the scene to build. And I can quickly demonstrate to you the effects of the environment probes and how they operate. Okay. And if I now build my project, I first have to enable USB debugging once again. My cable seems to be quite finicky right now, so it's disconnecting and connecting my phone constantly. Hopefully it won't happen during the actual upload. Yeah, that should also work. I don't know why I didn't consider it, but yes, that should also work. Usually it's better to make a prefab and then assign your values to the prefab, and then it will be applied to whichever objects you have that are tied to that prefab anyway. So that's a better form or better best practice to use instead of having the actual object in your scene. Let's see if it can build and generate the project. So if I run it now, you can see that the objects that I have in my scene, they are not black as they are in the editor, but they actually have some colors and some sort of a texture associated with them. And this is all sampled from my background environment. And these samplings, if I remember correctly, they update about every 10 seconds or so. And it's quite hard to manually assign new values to that updating or to lerp between the variables there, but it is kind of doable. So if you want a lot more realism, then that's one thing you can work towards. But for now, let's see if we can go on to a different topic and adding post-processing effects to our scene. So if we look at the demonstration I had here, then the environment probes had lighting, so it ties the scene together. And post-processing effects, they make the objects that you have in your scene slightly bleed into your background, which makes them more or less tie in much better. And especially if you add different forms of color manipulation on top of your scene, then it won't look as off when you look at it from your phone, especially when it's subtle, but it will tie the objects in your scene together with the actual environment that you're showing them in. And this can also have small effects to your application. So simple things like adding a little bit of blue light to the entire scene or washing it in blue makes it seem a lot cleaner. And adding a little bit of orange makes it seem a lot homier or warmer. So that all depends on what is your actual application or what you want to use it for. But I'll quickly show you how to actually add post-processing effects. Now, first, what we need to do is we need to go into our AR session origin and go into the AR camera. So the AR camera has these two lines here that we can set. And just to make our actions more visible, I will add a new object into the scene that does not have an actual surface or an actual reflective surface. So I'll create a sphere. And I'll make sure that it is pushed in front of the camera so that the camera can somewhat see it. Bring it ever so slightly closer. So at least we have a reference to an object in the scene. I'll also bring the reflective one closer. So now we have, these are the two things our camera currently sees if we start. And this is a good way to judge what the post-processing effects are doing to our scenario. I will also create another object here with an extra material. So I'll go into materials and create a new material. And this one I'll make into a light source. And the way to make it into a light source is we need to scroll down into emission and select a color that it will emit and the intensity at which we want to emit that color. And then we can assign it to our third sphere. I'll just adjust it so it's better in the frame. Now we have a reflective sphere, we have a normal sphere, and we have an emissive sphere. Now, looking at it right now, the emissive sphere does not really seem to blend into the environment that well because there is a very sharp and clear edge to it. No matter how emissive we make it, then it will still have this sharp and clear edge. And that's why we need to add post-processing effects that either bloom the emissive properties and tie light together just a little bit. Now, I can't really, the resolution of my monitor is quite high and you probably won't see it that well. But in the rendering pipeline, there's two things that we need to set. One is post-processing. This will allow us to set post-processing effects. So just to recap, this is an AR session origin AR camera. And the camera itself has a rendering property. There we need to set post-processing. And then we have anti-aliasing, and we can check fast approximate anti-aliasing. And if you apply this, then you will see that in your scene, your spheres or whatever objects you have will become much more smoother around the edges, and they won't have these jagged lines anymore. So this is what anti-aliasing does. Those jagged edges, they are named as aliases or aliasing, and anti-aliasing is removing those by blending them slightly together. Now, this is the simplest form of post-processing we can add. And next, we will add actual post-processing effects. So we'll take the same camera and we'll scroll to the very bottom and add a new component. Yes, I can repeat the materials for the two spheres. So for this sphere, I did not set any material. It's the default material if I spawn in a new sphere. And for the second sphere, in the materials folder, I create a material and I check the emissive property and just change the color here. And at the bottom, there's this intensity slider that you can set. And the intensity defines how much the material will emit light. If you have actual models that you start working with, then you might have small portions of the model being emissive while the rest isn't. And this is all you can do with combining different textures together and applying this in the shader generation yourself. But let's go back to the AR camera. I'll give you all, everyone a quick minute to catch up. Now, just a quick note, you don't actually have to move these objects to the specific location based on the camera. If I look at them already, they are already anti-aliasing is already applied here. So no matter if I look at it from the scene or the game window, the post-processing effects are still going to be applied. It's just that from the camera view, if you have some post-processing effects that only affect the camera space, then you can better view them here. And you can get a better understanding of what your phone will see in terms of what is layered on top of your actual background. If you want to do a lot more fine tweaking, then it's a good idea to add a photograph of the actual background in your scene as well, right behind the camera, and then you can do some fine tuning with post-processing effects. But for now, we have our AR camera. We have enabled post-processing and anti-aliasing. We can go to the very bottom and add a component. And we're going to add a component that is present in Unity by default, called a volume. And volume is something that handles post-processing effects. In the volume, we can set it to either global or local. Global volumes affect all cameras that you have in your scene. So if you want the post-processing effect to work overall in your entire project, and local volumes are things that you can attach to certain objects or locations. So they have a collider around them, and based on the collider, if the camera enters that collider, then the post-processing effect will take place. This is how I created that effect of blurring and grayscale image if you entered the sphere in the first day's demonstration that I showed of how you can create user interfaces. So that was done with volumes and post-processing effects. Now in the volume, we can create a new volume. And once we create the new, it will give us an option to add an override. If we click on override, it will only show us post-processing. And in post-processing, you have a whole list of different post-processing effects that you can apply. Now, not all of them will work on AR applications, but most of them you can apply. And it's more a matter of artistic understanding and how photography works, of how to get the perfect picture or how to modify the scene so it looks visually much more pleasing. So one quick thing that I can, for instance, do is add the bloom. And in bloom, I can check the intensity, the threshold, the scatter, and the tint. And if I start increasing the intensity and maybe changing the threshold, then you can see that in our reflective surface here, it is so reflective that it is instantly directing the light source of the scene directly into the camera. So this one is going to be very bright. And the light source that we created, this one has a slightly less intense light source, so it's bleeding everything around. So we can set the values here. We can even set the color of the bloom that we're creating. I'm just going to set this white, and I'm going to reduce the intensity a little bit so it's not as overbearing. I'll set this down a little bit. Okay. We add more components here. So post-processing effects like color adjustments, post-exposure, contrast, hue shifts, all of these things that you can change and play around with. So if you know anything about photo manipulation or simple Photoshop skills, then you are most likely familiar with a couple of these functionalities. So this is something that requires a bit of artistic merit. But these can be already applied very simply onto your scene. And I will try and demonstrate to you the effects of these if I build my project. I'll just press build and run, and it should build it. Okay. My scene should now be running. It hasn't detected anything yet, but as soon as it adds them, then if I move around the objects that I have here, then you can probably see that the light source that I added has a actual tint around it, so a blooming effect. And it is slightly more part of the scene compared to what it was previously. So it's not as separate as it was previously. Now, these post-processing effects, if you compare the one in the editor window with the one that I have on my phone, then you can see that on a completely black background, it is much more visible. So this does require a bit of tweaking. And this is why it would be a good idea to have an actual photograph behind your scene so you can better tweak the post-processing effects. Now, those are connections. For the second part of the workshop for today, this is going to be it. After an hour's break, We will come back and we will move on to a slightly more complicated topic, which is going to be light direction estimation. So there are functionalities in AR Core that calculate the intensity of the light and light direction, but this is not directly tied to any light source in your scene. So we're going to have to write a script that takes in all of those parameters and applies them to the scene. And after we have done that, we're going to have to create a script that actually displays shadows on our floor. And with that, we can also create a script that hides all elements in the scene that go below the floor. So we will cover light estimation, shadows, and occlusions. But for now, thank you for your attention and see you all after the lunch break. I will just quickly upload the project as well. There's the link, and after it has done uploading, then you can download it if you want. So we'll see you all after the lunch break.
Really nice. A to ci idę skać certyfikat.
Yes, I am here. Okay. Let me just share my screen. Okay. So I'll just start the project where I left off. So for the final parts that we're covering, we don't have to make a new scene, so we can keep the same scene that we had here. We're just going to be adding a couple functionalities to it. The first functionality that we can add is light estimation. So with the scene that we currently have selected, if we add a plane object into our environment and just move it under the scene or under the sphere, I need to make it so that it is a separate object entirely. I'll scale it back to its original size. And I'll move this slightly further down. It might actually be a good idea to have this at 0, but I'll keep it slightly down. So if we run our scene as is, then as you can see now, all of the objects that we have in the scene, they will start casting their own shadows. So for these shadows to be cast somewhere, you need some sort of surface to grab these shadows. A good test for us is just a simple plane object. If you have multiple objects in the scene, then they will start casting shadows on top of one another. But in order to increase the effect of realism a little bit and also make the objects that we have in the scene be lit up better, then we are going to add light estimation. So we're going to draw on the functionality of AR Core that takes in what it thinks the light direction is coming from. And we are going to write a script that applies those light direction parameters to our directional light in the scene. So that way the objects will look as if they're lit from the correct direction, with the correct color of light, with the correct intensity, and the shadows will also appear slightly better, especially if you have a surface detection already implemented. Now, what we need to do is we need to go into our AR session origin, and we're going to add a new component to it, which is an AR. Oh, sorry, we don't add it here. We actually go into the AR camera. So not the AR session origin, we go into the AR camera. And we have to add it here at the very bottom. And it should be AR light estimation. Or is it already? Ah, yes, light estimation is already added by default, but it's just disabled. So you don't need to add a new component. You just scroll up to the AR camera manager, and it has a light estimation module. Now, if we just enable this, So we enable everything. It has a couple of parameters here like ambient light intensity, color, harmonics, direction, and intensity. And depending on your version of Android or iOS or whatever you're using, the backend will give you different values to work with. So this will be different for iOS and this will be different for Android. But it will give you a list of parameters that you can work with, but it will not apply them to any light source in the scene. So for that, if we currently just enable this on everything, it will do all of those calculations for us, but it won't do anything with those calculations. So we now need to write our own script that takes in these component values and applies them to our directional light. So let's go into our scripts folder. Ground shadows, I just created a plane. So in the hierarchy, you can just create a 3D object, like a plane. Make sure it is not a child of any of the other objects that we already have. And then just make sure that the scale is 1, 1, 1, and position you can adjust accordingly. But this is just a simple object. I also take the spheres that I have and I'll put them inside of an empty object, so that clears our scene just a bit. But this way it's slightly cleaner than it was previously. And now we can create our script. And the script we'll be creating, I'll name it light estimation. Now in the script, we're going to have to get a reference to the light source. So not just the game object, but the actual light component of our light source. And we'll have to get a reference to the AR camera's AR camera manager script. So we will take all of the parameters calculated by the AR camera manager and copy them over to our directional light source. And since this script will be tied to our light source anyway, then I will make the script so that it is actually in the a component of the light source itself. So we don't have to have a public variable for the light source. But we need the imports that we usually have. So using Unity Engine, tar.ar foundation, and using Unity engine.start.subsystems. So we need these two to actually access the AR camera manager. Next, we're going to add two variables. One of them is going to be a reference to the light source, and the other one is going to be a reference to our camera. Sorry, the camera manager. So the camera manager will be a public variable that we can set. can also set this as a private variable and then do it on start, the enable by finding it in our scene. But I'll just make this public to show that if you don't want to do it in script, you can also pull these things from the scene. And then we need the light source. And then on the start method, we need to get the light component. And since I plan on adding this script to our light game object, then I will use the get component functionality. Otherwise, I would have to make the light here a public variable as well, and then manually assign the light variable. Now, just like we had with our image detections, we're going to do a very similar thing here. We're going to create a function, and then we're going to add it to our AR camera manager so that every time it gets an update for light estimation, it's going to start calling this function. So first, let's create our function. I'll just call it frame changed. And it needs an input of AR camera frame event arguments. So AR camera frame event arguments. Now we have the format of a function that we can give to our AR camera manager. So just like we did with the image tracking script, we're going to have an on enable and on disable function. And we're going to reference the AR camera manager, get the frame received functionality, and add our frame changed function to it. And on disable, we will just remove the function. So this way, every time the augmented reality experience at the backend is calculating and finds a new angle for the light source or a new parameter for the light, like the light color, then it will call this frame changed function and then apply those variables in our arguments. So now we have to go through all of the values that are put into the arguments, and if they are available, then we have to assign them to our light source. So this will be a long list of if statements. We have light estimation, and the first one is average brightness. And we just have to check if it has a value. So for each of these, we have to check if they have a value. And if they do have a value, then we can set the main light color or the main light parameters to those values. So the main light also has a variable called intensity. And we can just take this value that we checked. Instead of checking if it has a value, we will grab the actual value. So this will check if the algorithm has detected a light source and if it has a particular intensity value. Next, we can do a copy paste of this, and instead of the average brightness, we can check the average color temperature. And this will not be set into intensity, but it will be set into color temperature. Then next we have the color correction. So temperature is between the blue hue and the red hue, and color correction is between the red and purple. Let's see, what was it named exactly? Just color correction. Color correction value, and this is the actual color in the main light. Next, we can calculate the light angle. I'll copy this. And this time the light estimation will be main light direction. And this will be added into the transform rotation. So this look at function that we have here is because if we have a light source and it's looking at some specific direction, and we get a vector that says that the light is actually supposed to be in that direction, then it will calculate the angle so that this light source will be angled the same way. So you can't always just give it. This is more or less when you're trying to convert a vector into a quaternion. So we have a vector of where it should be looking at, and we want to get a quaternion so that the light source would look in that vector's direction. So that's why we need this quaternion look at rotation function here. Now there are a couple more things that we need to go over, and they are almost identical to the ones that we have previously. They are even overwriting some of the properties that we estimated previously. And these differences come in when you're using either iOS or Android. And personally, I haven't tested which ones of these are specific to Android and which ones of these are specific to iOS, as some of these might just be specific to different versions of Android. So we have main light color. So this is very similar to the color correction, and it will function the same way. It's just that depending on which one is given by the light estimation function. And if you're using Android, then this value needs to be changed just a little bit. We need to divide this by mathpi. And we need to apply the gamma value. If I remember correctly, then on iOS, you did not have to apply this extra calculation here. You just had to take this value straight out. So these are, again, small differences in implementations between different platforms. Next, we have the intensity in lumens. So average intensity in lumens. And for the main light, this is the same as just intensity. And finally, we can take the spherical harmonics. So this will be a different value. And for this one, we need to set the actual rendering settings of the project instead of setting any variables in the light source itself. So render settings, ambient mode. And then render probe, render settings, render probe. Ambient probe. And ambient spherical harmonics dot value. With this, we're going over each of the possible variables that our light estimation can give us. And now we can go back into our project. I will first send this script via the drive as well, since I can expect that some of you did not follow all of those texts. I know I would have trouble following that. So light estimation. The reason why I didn't send you the script just right away, but I went through it and wrote it with some of you, is that I'm kind of showing you what is happening behind the scenes. And later on, we will also modify that script a little bit. And I want you to understand what is happening there before we get into actually modifying it. Now, if you have the script in your project, you can go into the directional light that we have in our scene. And we can take the light estimation script and add it to our main directional light. This will also need a reference to the AR camera manager. So that one, we can just take the AR camera and drag it into the AR camera manager. And this will look up the AR camera manager component in our AR camera. And with this, if I run the project now, it should be able to automatically estimate the direction of our light source and update it accordingly. So yes, after you have the script, just drag it to the main directional light source and attach the AR camera to the one field it has that you can set. And there's nothing else that needs to be set since the script handles everything else. So it should finish building any second now. And now if I run my project, we have the plane there, and you can see the shadows. And these shadows are constantly moving and updating. So currently the plane is very high up for my case, since it initialized in the location where my camera was. But if you have the plane detection algorithm working, then you will have your ground plane in your actual ground. So we can just quickly set that up. We can go into our AR session origin. And just like we did with our start of the second day, we can add a AR plane manager. So this is the AR plane manager, and then we can go into our prefabs and take the AR default plane that we created last time and add this as well. So this way we will have some sort of a reference plane in our scene, but we will also have actual planes being detected in our final application. And I will just make this plane a lot smaller so it is not massive in my actual application. So it's only useful for testing out here in the editor. But the current implementation that we have just made, all of the light sources or light estimation that is happening, it is updating instantaneously. So if a new update happens, so let's say your camera is here, it sees that a light source is coming from this direction here. But then on the next frame, the calculation updates and says that the light direction is actually coming from here. Then that means if you have an object in front of the camera, then the shadow will be first in this location, and then it will jump to the next location. So it won't be a continuous smooth transition between multiple positions. It will be very sharp transitions from one point to another. So one way we can fix this, and to make our scenario seem a bit smoother but still use this light estimation, is we can go back to the light estimation script, and this quaternion here that we're calculating, we can save it in a variable. So I'll save this as a quaternion angle. Rectangle. And then we can apply a slower form of rotation so that it wouldn't be an instantaneous rotation between two angles. So for that, we can use a function in quaternion, the quaternion library called rotate towards. And if we look at this function, it takes in one quaternion, a second quaternion, and then it takes a degrees value of how much you should rotate from one of these to the other. And this is like a maximum number of degrees that should be rotated between these two variables. So this means that we can set our current position. So the main light rotation is the same here. Then on the next line, we can set our light angle that we're rotating to. And then finally, we can have some sort of a number that denotes how quickly we're rotating. And since this is going to be constantly updating, it's good to have some sort of a slower form of update. So I'll put a time dot delta time. And then just multiply this by a float, so it isn't excruciatingly slow. So what I'm showing you is that all of these scripts that we've made here, you can still edit them to get different sorts of functionalities or to improve the final results you can get from your scene. And we don't have to change anything from the script on the editor side because these are only small changes that were made inside the script itself. Now, the way we have the project currently set up, we have objects that are being placed automatically as soon as you start your project. We have a plane that is also being automatically set. We have these ground planes that are being detected, and all of these ground planes have the debug plane material. And in this case, this is a pink material, so it does not even have a proper material attached to it anymore. So if we actually run this program right now, then we'll see that all of the ground that is being detected will turn into this very bright magenta color. So what we can do is we can create a new material that will represent our ground. We can set all of the variables here so it would function more like our ground. And then we have to take the prefab that we have in our prefabs folder for the plane, and we have to set the material for it. So right now the mesh render in the prefab is set to debug plane, and we can either search for the material that we just made, which is ground, or you can go into the folder where the ground is and drag and drop it into the prefab. So this will update the prefab instantaneously. So if you later run the project, all new instances of this prefab will be updated. And we can also bring this ground texture to the plane we have in the scene, so they will look identical. But this ground texture does have a problem at the moment. This is a very opaque surface. So if we start detecting anything in our actual scene, then they will be covered by this very opaque plane. So all the ground, the surfaces, my tabletops, anything that I'm detecting with my augmented reality application will have this opaque layer put on top of it, and I won't see what is actually in the real world. Now, I can try and finick around with what the shader offers me. So I can make it transparent and try and change the alpha value to make it slightly more transparent. But if you see how this functions right now, if we make the plane transparent, then this also makes our shadows transparent. And this is for all of the box standard shaders that come with the universal render pipeline. So if we want to have our shadows being displayed on our floor, but we don't want the actual planes being displayed, then we need to write our own shader. Now, looking at how much time we have left, I will, instead of actually writing a shader from scratch, I will take a shader that I have pre-prepared, and I'll try to at least walk you guys through what it does. So I will put this shader in my project, and I will also upload it to the drive as well as the updated version of the light estimation script. So I'll give you all a couple of minutes so you can set everything up so that you have the AR session origin with a plane manager. You have the plane prefab attached, and you have a material that is attached to the plane prefab that you have customly made. And make sure you also have both the light estimation and the shadow script. The light estimation needs to be attached to the directional light, like I showed, but the shadow script does not need to be attached just yet. I will be first covering what is inside that script, and then we will go into actually using it. Okay, so if we all have the scripts, the light estimation script already attached, and you guys have downloaded the shadow shader, then I'll quickly open up the shader itself. So all of the scripts that we have been writing thus far have been in C#. So it's a object-oriented language that is similar to most languages that we might be familiar with. So it's similar to Java or C or C++ or Python. So it's a very familiar language. The shader, however, is written in a language called HLSL. And that is a type of language that is used for developing kind of a render pipeline. So how you want to use your GPU in order to render specific parts in your screen. So HLSL means high-level shader language, and it's the main one used by Windows. But the language is so well known that it's used by other interfaces as well that apply shaders. So the shader language itself is comprised of a couple different parts. The very first row that we have defines what is the name of the shader in our project or how we can access it. So that means it is going to be under a custom folder named shadow. So this means if we go into our assets, materials, and our ground, and go to this shader selection here, it is cross-platform. So HLSL is something Unity uses quite a lot, but it was originally meant for Windows. So Linux can still use it, and also Android can use it. It is just the main shader language. In the material that we have for the ground, we have the shader option here, and that custom shadow that we had means that it's going to be under custom and under shadow. So this way we can select the shader that we have. Now, next, the shader has a couple of properties. So these are things that we can give to the shader from our editor. So if we want to change the shader via giving it a different color or giving it a texture and stuff like that, they are going to be under this properties tab. So like we had with the different materials, all of these metallic, opaque front, and these base map and stuff like that, these are properties inside the shader that it's going to be used. So they're like variables coming from the outside. And then we get to the actual shader itself. So the shader itself has a couple of presets that you can set. In this case, these are presets, so it would be a transparent plane, but it is going to cull all objects that are behind, oh, sorry, here it is. So it's going to cull all objects that are behind it. This means it's partially a transparent shader, but at the same time, it's a transparent shader. So what that means is for rendering, you can see through it and it's transparent, but it is opaque in the sense that if anything is behind it, then it won't be rendered, or it will be culled in the culling point for the renderer. Then we have imports that we don't need to care about. And then we get to the actual vertex and fragment shaders. And shaders, since they operate on the GPU, then every single function here is going to be executed in parallel. So we don't have a reference of this function will be executed for this pixel first, and then for this pixel, and then for this pixel. All of these are happening in parallel, some of them being calculated faster than others. And because of that, there are two functions here. First is the VTech shader. So this one, if you have a polygon in your scene, so like we have this mesh here, if I show the wireframe of it, then it has these polygons. And the VTech shader goes through each of these vertices and does a couple of calculations. So these are things that you can assign yourself. And after all of these vertices have been gone over, then it will go into the fragment shader. And the fragment shader looks at every point in this surface and renders each of those separately onto your monitor or render output. Now, in the vertex shader, a couple of variables have been set here, so we could calculate the direction of shadows, but I'm not going to mention those very much in depth. And in the fragment shader, we are taking that 1 pixel value for the shadow. So we're checking if there is a shadow in a location or not. And we're applying that to the alpha value of our final texture. So the alpha denotes if it's transparent or not. So if a alpha is 1, then it's completely opaque. If it's 0, then it's completely transparent. And with the shadows, this works that everything that is not shaded will be white, and the shadows will be zeros. And if we invert those colors, then the shadows will be all ones, and the rest will be zeros. And if we put that into the alpha channel and set everything else to be black, then our shadows will be black, and the rest of the scene will be transparent. So that's how we can get both the shadows and the culling to happen for the scenario. Now, since those currently use properties that are specific to the AR rendering system, so how the background works, then this will behave very weirdly in our scene. So the transparent material that only renders shadows, you can see that it has these black dots that are being rendered, and those are going to be the shadows. And the reason why everything else here is so finicky and acting like that old, if you played solitaire on Windows and won, then you got those weird layering effects. And this is very similar to that. And this is just happening because the rendering buffer is not being refreshed afterwards, because the rendering buffer thinks that this is currently empty. And for our augmented reality experience, this means that it's completely transparent and it shows our real life background from the camera. So the way we have set it up currently, we can just go into our project now and try and run it on our devices. So I will first need to set up USB debugging. I should have my phone here, and I'll build this project.
So it's now copying the project. And now if I run it, my application will detect the floor, and those cyan lines that you can see are the plane detection working. And then on those planes, I am rendering these black shadows. Now you can change the rendering script so that the shadows aren't just black, but you can have actual colors associated with them. But currently I just set them to black. So otherwise you could set them so they are more or less transparent. And additionally, you can see that in my scene, the light direction is being estimated and the shadows are slowly moving to their correct locations and not just popping from one location to another. So these are just a couple of oh, there's one thing I did not show you right now. And I'm not sure if I can show you very easily. And that is occlusions. That will require me to detect an extra plane. It doesn't want to detect it. So currently, oh, you can see with some of the spheres that we have in the scene, or you could previously, and that is when they intersect with the ground, then they get occluded and become transparent behind the actual ground plane. So this is useful if you want to make planes, or if you want to hide objects that are under your table, for instance, if you're making an application that is supposed to be run on tabletop, or if you want to hide things that are supposed to be in another room while you have already detected the walls in your application. But these are just a couple of base systems that you can use to create augmented reality experiences. There are a lot more functionalities associated with it, and every single year, Google and Apple are coming up with new functionalities for AR Core and AR Kit that can be used. And with all of the new additions with newer smartphone models, they come stocked with cooler sensors that can also be used for augmented reality. So things that come to mind are the latest versions of iOS come with depth sensors. So those can be used to get a much sharper mesh of your actual room, or you can do much more accurate occlusions in your scenario and stuff like that. But essentially, in terms of how much I can teach you in this workshop, this will be it. I do employ that if you plan on making any Android projects, or if you are interested in it, then do try and tinker around with augmented reality. There are many cool things that can be implemented in it. And if not augmented reality, then you can always make 3D applications. And for those of you who have done 3D development before, let's say developed your own games or something, and you're thinking of augmented reality development, then there are only a couple things that are different between the two. The main thing is the amount of computational power you have when it comes to augmented reality. But this is it from me. And if you have any questions, now is a good time to ask. Otherwise, thank you very much for your attention and patience.
Thank you, Eric, for everything.
I will also upload this project as well. So if you missed some of the last parts, then you can still run with this project and see what everything there is. And I don't recommend using what I made as your base for a new project. It's good to start from scratch. But if you want to test out something, then that is all right. It's just some of the things I simplified down, and they're not completely optimal in their implementations. And for those of you who want to continue in some direction and want to know what to do else, then I suggest learning 3D development and computer game development, because those and augmented reality are very much related. So I have uploaded the final project to the Google Drive. And I guess that's it from me. Bye, everyone.